Suppose a model predicts the next hourly sensor reading. You shuffle the rows, make a train test split, and get a beautifully low error. Then you put the same rows back in time order, and the error jumps. The model did not change. The question did. Your first test let the model learn from neighbors that would still be in the future at deployment. Forecasting asks for the value after the latest timestamp. Interpolation asks for a value between observations that surround it. A random split can quietly turn a forecast test into something closer to interpolation because training rows appear on both sides of each test row. That can make a model look smarter than it is when the real job is to move forward through time. Here is the same timeline with blue training rows and orange test rows. Notice how the colors alternate. An orange test point can sit between two blue points, and a later pattern can be represented in training before the earlier test point is scored. The score is not meaningless. It is answering a different estimand. How well can we predict a randomly held out row from a mixed timeline? Now keep the first part for training and hold out a future block. In this controlled illustration, the signal changes level in the future. The random split reports an illustrative MAE of 0.16. The chronological split reports 0.63. Those are not benchmark results. They show why the honest test can look worse. It finally contains a change the past did not reveal. One future block is still a fragile verdict. Rolling origin or walk forward. Backtesting repeats the same action. Train on everything available up to an origin, predict the next step, move the origin forward, and record the error. The training window can expand, or it can roll. Hinman describes this as time series cross-validation because every test prediction is made from the past only. A feature window and a forecast horizon can overlap the boundary. If a feature uses the last 20 observations and the label is several steps ahead, rows right next to the test block may still carry information across the split. A gap, sometimes called an embargo, removes that boundary strip. In scikit-learn's time series split, gap is the number of samples excluded from the end of each training set before the test set. The split is not enough if pre-processing has already seen the future. A scalar fit on the entire timeline knows the future mean and variance. A rolling feature computed with centered or future values can do the same. Fit every transformer and every feature recipe on the training history available at that origin. A pipeline is a practical way to keep that boundary visible. Real series drift, repeat seasons, and change regimes. Cerqueira and colleagues show why performance estimation methods matter on dependent, non-stationary series. Tashman reviews repeated rolling origin tests for forecasting accuracy. Do not let one convenient split carry the whole claim. Compare several future windows, keep a simple baseline, and report the spread as well as the mean. Before you trust a time series score, write down the forecast horizon, the timestamp cutoff, the split, any gap, the feature cutoff, the baseline, and the metric. Then ask one blunt question. Could this input have existed at the moment the prediction would have been made? If not, it does not belong in that fold. Shuffling is not automatically forbidden. But for a past-to-future forecast, shuffle does not equal forecast. Keep the arrow pointed from past to future.